Hi dear friends, and welcome to this our session today. Today I came forward with a question that was proposed to me by a student. The question is based on algebraic structure. If we saw the question well, the question was saying that S is the set of all real numbers exist one, and the binary operation star on the set S is defined by A star B, which is equal to AB minus A minus B plus 2. They said show that S is an abelian group and explain why 1 must be excluded from the set S. Now, when we hear about the word abelian, what exactly can come to our mind? We should understand that for a set of elements to form a group, there are certain properties that we must verify to know if they hold or not. If they hold, we conclude. In the first place, it should be associative. It should what? It should have an inverse, and it should also have what, an identity, and it should also be closed. I'll take it again. It should be closed, right? There should exist an identity element, and all the elements must have an inverse, that is the inverse. And what is again? And it should what? It should be associative. So we just have to test all these properties. But since the question now is telling us that we should show that it forms an abelian group, means we must also test for the property of commutativity, because those groups that are commutative are called abelian groups. So if this group is associative, if this group is commutative, that ever means that we can conclude that it's an abelian group. Since they have given us our A star B to be equal to AB minus A minus B plus 2, so let's just start with the first one. Let's just start by looking for the identity. Let's verify if it has an identity element. Let's verify, and we have to use our definition of identity. We know that any element, let's take the element to be A star, its identity, let's call the identity element E. If it's commutative, that ever means that this should be the same like E star its star, the element, which that should give us what? A. So let's start with A star E. A star E, according to this, according to our A star B equal to that should give us A. Our B is E, AE minus A minus E plus 2. That should give us what? Still A. Good. Remember, I'm solving for E. I want to get the identity element E. That therefore means that I'm going to make E the subject. I'll bring the E's together. I'm going to have E, then I'll factor it out. I'm going to have A minus 1. That is equal to, I'll bring this A this way. It becomes what? It becomes 2A, right? 2A minus 2. So this is going to be 2A minus 2, right? All that on, okay, 2A minus 2, great. That therefore implies I'm going to divide out by A minus 1. This is going to be, that implies, this is an implication, please, that's an implication. But I'm going to have E to be equal to, I'll factor out 2 for me. I'm going to have 2 into A minus 1, all that on A minus 1. We see that this and this, they can cancel, right? Then I strictly have my answer to be 2. That ever means that the identity element in this case is 2. So let's verify to see if A star E is the same like E star A. Let me see E star A. I'm doing this because the question did not just tell us to show that it is a group, but it's an abelian group. So we have to test if it is commutative. That means I'm going to have, in this case now, my A is what? My A in this case is E, and my B is A. Therefore, I'm going to have, in this case, I'm going to have A. Oh, no. I'm going to have E, then B is my A, minus, what is my A? My A is E, minus, what is my B? My B now is A, plus 2. That should give me what? Still A. That therefore implies I'm going to factor out my E in this case. I'm going to have A minus 1. This A goes that way, becomes 2A minus 2. So this is going to be 2A minus 2. Implies I'm going to factor out my E. I'm going to have E into A minus 1, which is the same like what? 2 into what? Into A minus 1. Great. I have A minus 1, it can cancel. So I just have my E to be equal to 2. So since A star E is the same like E star A, I can conclude that the commutative property holds. Commutative property holds. and hence I have my identity element which is unique. Yes, great. That's the first property that we've tested. Now let's verify to see if there exists an inverse element. Let's call the element A inverse. Okay, yes, and we know that for the inverse element to exist, any element star the inverse, that should give us what the identity element. So I'm going to have my A inverse star A, that must give me the identity element E. That therefore implies I'm going to work based on this my definition here. My A in this case is my A inverse, so I'm just going to have A inverse, my B is A minus A inverse minus A plus 2. That should give me what? E. What is my E? My E, I got my E to be 2, so it's going to be 2. And I can see that these 2 and these 2, they can clearly cancel. That therefore implies I'm going to factor out my A inverse here. I'm going to have A inverse into, I have A minus 1. That is equal to what? This negative A goes away to become what? A. Wait. Then I'm going to divide all through by A minus 1. Implies I have my A inverse to be the same as what? A over A minus 1. And if we want to get the domain of this A inverse, we are going to restrict that this denominator should not be equal to 0. So if we do that, we are going to say our A should not be the same like 1. So we have not just found the inverse of this element, because the inverse of the inverse element is given as what? Is A over A minus 1. And the domain of this inverse element is what? Is all values of A, or better still, all the elements that are belonging to the set S excluding 1. Because if, let's take for instance that if this A becomes 1, therefore I'm going to have what? 1 over 1 minus 1, 1 over 0, which is undefined. Great. So that's the explanation that you're supposed to give to show that 1 must not be included. Wait, so we just found the identity element, we found the inverse, and we explain why 1 must not be included. So let's now move forward now to verify if at all, if the group S is associative. Let's now see associativity. Let's see, remember our A star B is given as A B minus A minus B plus 2. For associativity to exist, I can pick 3 elements at random. I can pick the elements, let's say, suppose A, B, C, they belong to the set S. If associativity holds, that means that A star B star C in this order should be the same as A star B star C in this order. Yes, it should be the same like this. It should be the same. This property should hold. Great. So let's verify to see if the property holds. Let's start with the first one. A star B star C. In this case, that is going to give us my A in this case still remains A. So I'm going to have A. What is my B? My B in this case is B star C. Then minus A again minus B star C. B star C. Therefore now plus 2. So implies I'm going to have my A. What is B star C? B star C in this case is going to be BC minus B minus C plus 2. Then minus A minus BC minus B minus C plus 2. Then plus 2 again. Plus 2 again. So if I simplify that, I'm going to have my ABC minus AB minus AC plus 2A minus A minus BC plus B plus C minus 2 plus 2. Great. Minus 2 and plus 2, they can already go to 0. They can already go to 0. That therefore implies I'm going to have now my ABC minus AB minus AC. 2A minus A gives me A plus A minus BC plus B plus C. Great. So that is A star into B star C. So let's verify if it is the same as A star B star C in this order. Yes, in this order. Let's verify. This is going to give us our A in this case is what? Our A star B. Therefore, we're just going to have A star B. We multiply that with C. A star B, so C minus A. What is our A? Our A is A star B minus B, which is what? C plus 2. Great. So implies we are going to have, what is our A star B? It is AB minus A minus B plus 2. So we are going to have AB minus A minus B plus 2. All that we multiply it with C minus AB minus A minus B plus 2 minus C then plus 2. Great. So this guy now turns out to be, we open up the bracket, we're going to have ABC minus AC minus BC plus 2C minus AB plus A plus B minus 2 minus C plus 2. Great. I'm sorry the 2 is not too visible, but at least you can see now. Yes. Therefore, we can simplify this one further as ABC. Then I'm going to bring this AB here. I'm going to have minus AB, then AC minus AC, then in this case I have A, right? I have A here, and let me see if I have another A again. I don't have another A, so it's just going to be this plus A, then plus this BC minus BC, then plus this my B here plus B, then plus my let's see, this is 2C minus C, which just gives me what? C. Then this negative 2 and plus 2, they cancel. So this is what I have. We can clearly see that this is the same like this, right? Therefore means associativity holds. Great. Associativity holds. Now we can clearly state that S is clearly closed. S is clearly closed since this AB belongs to the set S, ABC still belongs to the set S, and AC, in fact all the elements, S is clearly closed since no new element is involved. No new element is involved. Great. Is involved. Great. So we have tested that the group is we have tested that S is what? That S has an identity element, right? And we saw that to be what? And we saw it to be A over A minus 1. And we explained why 1 cannot be included. And we also found what in fact, we saw the inverse, right? We also saw the identity element. We have been verifying that this set is associative. And we also showed that it was commutative, right? Great. And we also showed that it is closed. So we can say that hence S star like this is abelian. Yes. So thank you very much for watching the video, and I look forward to see you in the next. And please, just for a quick reminder, if you're new to our channel, please subscribe to our channel to get authentic solutions to all your questions. And feel free to email me. Okay, feel free to email me, and I'll also drop my WhatsApp contact in the description below so that you can get to me each time you have problems in biology, chemistry, physics, mathematics, further mathematics, additional mathematics, even some of them on computer science. Okay, yeah, so